in this lecture, we shall discuss some spectral properties of the graphs. We shall start with the definition of an adjacency matrix. So let's write the definition of adjacency matrix here. Adjacency matrix of a graph. So how do we define adjacency matrix? Let G be a graph with vertex set of G is equal to V1, V2, so on, Vn. That means we are taking a graph of order n and edge set E of G. It is equal to E1, E2, so on, En. Then the adjacency matrix. The adjacency matrix of G is an n cross n matrix, where n is the order of the graph, is an n cross n matrix denoted by A of G, or simply A, and is defined as A of G is equal to Aij n cross n, where Aij is equal to 1 if vertex Vi is adjacent with vertex Vg, and this is equal to 0 if Vi is not adjacent with Vg. So this is how the adjacency matrix of a graph is defined. It is an n cross n matrix where n is the order of the graph, and the ijth entry in this adjacency matrix of G is defined to be equal to 1 if the vertex Vi and Vg are adjacent. Otherwise, the ijth entry of this matrix is defined to be equal to 0. And throughout, we will assume this graph to be simple graph. That means a graph without loops and without parallel edges. So once we have a graph which is a simple graph and which is without loops, without parallel edges, then it obviously means that the diagonal entries of this adjacency matrix will always be equal to 0. So let's take an example. Let's consider a graph. Consider a graph G that has this kind of a structure. Suppose we will take it like this. Suppose this is our graph. Let's call the vertices as V1, V2, V3, V4, and V5. Then clearly by definition, the adjacency matrix A will be a 5 cross 5 matrix. So adjacency matrix of G, it is a 5 cross 5 matrix where the rows and the columns are labeled by the vertices. So therefore, the rows are labeled as V1, V2, V3, V4, and V5. And similarly, the columns are also labeled by the vertices. It is V1, V2, V3, V4, and V5. Now the ijth entry is defined to be equal to 1 if vertex Vi is adjacent with the vertex Vg. Now obviously, since the graph has no loop, so therefore V1 is not adjacent with V1, so therefore this entry is equal to 0. Now here in the graph, we can see that V1 and V2 are not adjacent, so this entry is equal to 1. Now V1 and V3, So sorry, this entry is equal to 0. Now V1 is adjacent with V3, so this entry is equal to 1. V1 is not adjacent with V4, and also V1 is not adjacent with V5. So therefore, these two entries are also equal to 0. Now, observing here that whenever we have two vertices Vi and Vj, if they are adjacent, then Vi is adjacent with Vj, but we can also say that Vj is adjacent with Vi. So once any two vertices Vi and Vj are adjacent, then we have by definition that ijth entry is equal to 1. But at the same time, Vj and Vi are also adjacent. So therefore, the jith entry will also be equal to 1. So keeping this observation in mind, we can see that this matrix, adjacency matrix, is always a symmetric matrix. So if we have this as our first row of this matrix, then obviously the first column must be the same one. So the first column is 0, 0, 1, 0, 0. Now this is the entry A2, 2. Again, this is equal to 0. Now we will check if V3 and V2 are adjacent. Now V2 is adjacent with V3. So here we have 1. V3 is adjacent with V4 and also with V5. So here this is equal to 1, and this is also equal to 1. So V2 is adjacent with V3. It's also adjacent with V4. So actually we have made a mistake here. So here we are actually calculating what is V2 adjacent with. So here V2 is adjacent with V3. V2 is not adjacent with V4. And V2 is also not adjacent with V5. So here we have these as entries, zeros. Now again, the second row and the second column must be identical. So this is 0, 0, 1, 0, 0. Now here we have the entry A33, that's again equal to 0. Now we have to check what is V3 adjacent with. Now V3 is adjacent with V1, we have the entry 1 here. V3 is adjacent with V2, we have the entry 1 here. Now V3 is also adjacent with V4 and V5. So again, we have 1 and 1 here. And obviously here we will get 1 and 1. Now this is the 4 entry, this again equal to 0. And now here for this entry, we will check whether V4 and V5 are adjacent. Now V4 and V5 are adjacent, so we have 1 here. V5 and V4 are adjacent, we have 1 here. And V5 is not adjacent with V5, so we have 0 here. So this, therefore, in this way, we can construct the adjacency matrix. So let's write certain observations that we can clearly see. Observations. The first observation is whenever Vi is adjacent with Vj, we have Vj is adjacent with Vi. So thus, the adjacency matrix is always a symmetric matrix. Is always a symmetric matrix. And also the second observation, we can see that now here the vertex V1 is adjacent with V3 only. So therefore we have one non-zero entry in the first row, and obviously we will have one non-zero entry in the first column. Now similarly V2 is adjacent with V3. So again we have just one non-zero entry in the second row and the second column. Now V3 is adjacent with all the remaining 4 vertices. So therefore we have 4 times non-zero entry in the column and the row corresponding to V3. So actually what we want to observe here is that the number of non-zero entries in any row or in any column is equal to the degree of their corresponding vertex. So the number of non-zero entries in ith row and ith column, ith row or column is equal to the degree of the corresponding vertex. Degree of the corresponding vertex Vi. Corresponding vertex Vi. And then the third observation. As we know from the matrices of graphs, a matrix obtained by permutation of rows, permutation of rows or columns of the adjacency matrix AG corresponds to the relabeling of the vertices. Corresponds to the relabeling of vertices of G. So if we permute any two rows or if we permute any columns, any number of columns, then the new matrix obtained from A of G will be actually permutational similar to the original adjacency matrix. So thus, any two adjacency matrices, thus any two adjacency matrices of a graph G are permutational similar. Permutational similar. Because if we change the labeling of the graph, we will get a new adjacency matrix, but that new adjacency matrix will be permutationally similar to the original adjacency matrix. So therefore, if we either interchange, if we either permute the rows or columns, then the new adjacency matrix will correspond to the new labeling of the graph. And if we differently label a graph and then construct the adjacency matrix, we will get the adjacency matrix which can be obtained from the original adjacency matrix of the graph by just the permutation of rows or columns. So therefore, when any two adjacency matrices of the graph are permutational similar, so therefore, they share the same spectral properties. They share the same spectral properties. So why do we write this observation here? Actually, whenever we are given any graph, then we can take any adjacency matrix of that graph and then study its spectral properties. Then any other adjacency matrix will have the same spectral properties. Now, certain more observations. Observation number 4. As we have seen that the diagonal entries of the adjacency matrix are all equal to 0. If A of G is the adjacency matrix if A of G is the adjacency matrix, then all diagonal entries are equal to 0. All diagonal entries are equal to 0. That is, trace of the adjacency matrix A is always equal to 0. So, but we know that the trace of the adjacency matrix is equal to the sum of the eigenvalues. So thus, sum of all eigenvalues, the sum of all eigenvalues of A is always equal to 0. always equal to 0. Now again, we know from the matrix theory that the trace is the sum of all 1 cross 1 principal minors. But from matrix theory, we know that, trace of A is the sum of all 1 cross 1 principal minors. One cross one principal minors. So thus, sum of all 1 cross 1 principal minors. Principal minors of adjacency matrix G is always equal to 0. In fact, we can clearly observe that a 1 cross 1 principal minor is just the diagonal entry. So the first 1 cross 1 principal minor is the first diagonal entry A1, 1. Then the second 1 cross 1 principal minor is the second diagonal entry, that is A2, 2, and so on. And since all the diagonal entries are equal to 0, so therefore the sum of all these 1 cross 1 principal minors in an adjacency matrix is always equal to 0. Now let's look for the sum of all 2 cross 2 principal minors. Now, since in an adjacency matrix, if we take any 2 rows or any 2 columns, then since every row corresponds to some vertex and every column also corresponds to some vertex. Thus, if we choose any 2 rows, then those 2 rows will correspond to some 2 vertices. So let's make this as our observation number 5. Now let I is not equal to j. Then the principal minor of A obtained by the ith and jth rows and columns of A is either has this kind of a shape. It is either 0, 0, 0, 0 if Vi is not adjacent with Vj, or is 0, 1, 1, 0. And this is the case if Vi is adjacent with Vj. So therefore, we have 2 cases. There are 2 different kinds of principal minors when we choose the ith and the jth vertex. So therefore, the principal minor obtained by choosing the vertex Vi and the vertex Vj, that means the ith row and the jth row. And similarly, the ith column and the jth column, then the principal minor so obtained will be a 2 cross 2 submatrix of A of G. Then its shape is either all the elements are equal to 0 if Vi and Vj are not adjacent. Otherwise, if Vi and Vj are adjacent, then it is equal to 0, 1, 1, 0. And now in this case, we can see that the determinant, if Vi and Vj are not equal to 0, then this principal minor corresponding to the vertex Vi and Vj is singular. But if these 2 vertices Vi and Vj are adjacent, then the principal minor that has this kind of a matrix form has value equal to 1. So now determinant of this matrix 0, 1, 1, 0 is equal to minus 1. And whenever we have this kind of a principal minor, that will be actually corresponding to the vertices which are adjacent. So this kind of a minor, this kind of a non-singular minor, in fact having determinant equal to 1, minus 1, having determinant equal to -1 is obtained whenever the two vertices Vi and Vj are adjacent. So therefore, if we take all the principal 2 cross 2 minors, whenever we get this kind of a minor, we have the determinant equal 0, and the two vertices Vi and Vj will not be adjacent. But if we get this kind of a principal minor, then we see that the vertices will be adjacent and the value of this matrix is equal to -1. So therefore, what we observe, therefore what we get, therefore the sum of all 2 cross 2 principal minors therefore the sum of all 2 cross 2 principal minors of A of G equals minus times the cardinality of the edge set, minus times the size of the graph. So this was observation number 2. Now, similarly, if we take the 3 vertices now the observation number 6. Consider principal submatrix. Consider a principal Okay, now consider a principal submatrix of A of G formed by 3 vertices Vi, Vj, and Vk. Then we consider the following cases. Then we have the following cases. Now we will look for the induced subgraph induced by these 3 vertices Vi, Vj, and Vk. Either the induced subgraph induced by Vi, Vj, and Vk is a connected graph or it is a disconnected graph. So keeping that thing in mind, we will take the following cases. Case number A will be if the induced graph induced subgraph formed by vertices Vi, Vj, and Vk is disconnected. Then either the graph that is induced by these 3 vertices is a totally disconnected graph, that means it only contains the 3 vertices and contains no edge, or it is a union of K1 and K2. So therefore, there are 2 different ways as how this graph can be disconnected. So either the graph will look like this. So this is Vi, Vj, Vk. Or the graph will have some edge, or it will have this kind of shape. For example, Vi is here, and there is an edge between Vi and Vj and Vk. So either the graph will have this kind of a shape, or the graph will have this kind of a shape. But in both the cases, if the graph has this kind of a shape, then the adjacency matrix, which is the submatrix of the A of G, then the adjacency matrix so induced by these 3 vertices will be a 0 matrix because there are no adjacencies between these 3 vertices. So if we have this G1, which is the subgraph induced by these three vertices vi, vj, and vk, then the adjacency matrix, if the induced subgraph, if the induced subgraph is G1, then the submatrix obtained from A of G induced by these three vertices, we shall denote it by A of G1. Now this will be a zero matrix, 0, 0, 0, because there are no adjacencies between any pair of vertices. But if the induced subgraph is G2, and we shall call this graph as G2, then the adjacency matrix of this graph shall be denoted by AG2. Now by definition, since this vertex VI is not adjacent with any vertex, so let's name the rows as VI, VJ, and VK, and the columns as VI, VJ, and VK. Then, since this VI is not adjacent with any other vertex, so therefore the first row will be equal to 0, and in fact the first column will equal to 0. Now also the diagonal entries are all equal to 0, and VJ and VK are adjacent, so therefore this is the induced adjacency matrix induced by this kind of disconnected graph, which is induced by the vertices VI, VJ, and VK. And we can see that in both the cases, these induced adjacency matrix formed by these three vertices VI, VJ, and VK is a singular matrix. So in both cases, the matrix formed is the adjacency matrix. On VI, VJ, VK is singular. So this was the case when these three vertices induce a disconnected graph. Now the next case is if they induce a connected graph. So let's take part number B. Now suppose the graph induced by VI, VJ, and VK be a path defined in this way.
It's 2 o'clock.
Is adjacent with VJ, and this is adjacent with VK. So therefore, the induced graph will look like this. So this is equal to VI, this is VJ, and this is VK. Then the submatrix. Then the submatrix of A of G induced by the vertices VI, VJ, and VK is, let's call it this graph as, suppose H is adjacency matrix of H. In fact, this is a submatrix of A of G. Now this will have this kind of a shape. In fact, since this vertices VI and VK have exactly the same properties, so they will have this. Therefore, their rows or the columns in the adjacency matrix will be identical. So this is suppose VI, this is VJ, and this is VK. This is VI, VJ, and VK. Now the diagonal entries are all equal to 0. Now VI is adjacent with VJ, so here we will have 1. VI is not adjacent with VK, so here we will have 0. Now VJ is adjacent with both VI and VK, so therefore we have 1 here. And in fact, we can clearly see that the columns or the rows corresponding to VI and VK, the first row and the third row are identical, and in fact the first column and third column is also identical. This was because these Vi and Vg, they share the same properties in terms of their adjacency in this path Vi, Vj, Vk. So clearly the adjacency submatrix, the submatrix so obtained is again singular. So we have taken first two cases. If the inducer subgraph is disconnected, then the 3x3 principal minor is singular. And again, if it is connected but it induces a path, then again the 3x3 principal minor obtained from the adjacency matrix is again singular. Now the last case is case number 3. If the inducer subgraph is a triangle, if the subgraph induced by Vi, Vj, Vk is a complete graph on 3 vertices, that's a triangle, then the principal minor induced by these 3 vertices that the principal minor induced by these 3 vertices is, and it has this kind of a shape. It is a adjacency matrix of a complete graph on 3 vertices, so it is 0, 1, 1, 1, 0, 1, and 1, 1, 0. Only the diagonal entries will be equal to 0, and all the remaining entries will be equal to 1 because any pair of vertices is adjacent. Now the determinant of this matrix is equal to 2. The determinant of this matrix is equal to 2. So what we obtain from here, thus the sum of all 3x3 principal minors there's the sum of all 3x3 principal minors of adjacency matrix of G is twice the number of K3s in G. That is twice the number of triangles in G. So what we have observed, first we observed that the trace of this square adjacency matrix is equal to 0. So therefore the sum of all 1x1 principal minors is equal to 0. Now the sum of all 2x2 principal minors, that is minus times the number of edges. The sum of all 2x2 principal minors is minus times the number of edges. And now the sum of all 3x3 principal minors is equal to twice the number of triangles in G. So let's conclude this in one statement. So the conclusion is a kind of a result, so let's call it a lemma. If G is a graph of order n greater or equal to 1 and size m, then the first observation is trace of the adjacency matrix is equal to 0. The second observation is the sum of all 2 cross 2 principal minors. The sum of all 2 cross 2 principal minors is equal to minus times the cardinality of the edge set of G. So, which is equal to minus times M. And the third observation is, the sum of all 3 cross 3 principal minors is equal to twice the number of triangles. Twice the number of triangles. Now we define the characteristic polynomial of a graph. Now a definition. Characteristic polynomial of a graph. Characteristic polynomial of a graph. So how do we define a characteristic polynomial of a graph? If G is a graph, of order n, then the characteristic polynomial of adjacency matrix of G is known as the characteristic polynomial of G. Characteristic polynomial of G. This is denoted by C characteristic polynomial of G in the scalar lambda, which in fact we know from the matrix theory, it is defined as now the determinant of the adjacency matrix of A minus lambda times I. Now the spectrum of G is the set of eigenvalues. Is the set of eigenvalues of the adjacency matrix, which is denoted by spectrum of G and defined as in this way. This is spectrum of G. This is equal to a set, this lambda 1, M1, lambda 2, M2, so on, lambda k, mk. Or this is also written in this way. This lambda 1, M1, lambda 2, M2, so on, lambda k, mk, where lambda 1 to lambda k are the distinct eigenvalues of A of G, and mi denotes the multiplicity of lambda I. Multiplicity of lambda I. So therefore here, lambda 1 power m1 means that lambda 1 is the eigenvalue of adjacency matrix repeated m1 times, and similarly so on. Now here this is the permutation form. Lambda 1 is repeated m1 times, lambda 2 m2 times, and lambda k mk times. So we conclude here.